Welcome back and welcome to the video on the electromagnetic spectrum. We often short electromagnetic to EM, so if you see that, that's what it means, the electromagnetic spectrum. Now, in terms of what that means, electromagnetic, you don't really need to know anything at this level, but just to kind of explain it, the way these waves travel, and we'll see the names of some of these waves, and one of them is visible light, so how you're seeing this screen right now, is by fluctuations or just oscillations or vibrations in the electric and magnetic fields. That's where it gets this name from, electromagnetic. So electromagnetic fields are involved. You might remember the magnetic fields from previous years, iron filings lining up to show you that shape. Now what do you need to know? You need to know the main features, so we'll talk about the groups in a minute. You also need to know that they all travel at the same speed. So we'll mention that just a bit now. Well, all these waves you see in a minute all travel at 3 times 10 to the 8 meters per second in a vacuum. In air, it's very similar. You might remember the refractive index of air is about 1, approximately equal to 1. So in air, light also tends to travel, all electromagnetic waves tend to travel at that speed too. As we go higher into water and glass, we know they slow down because remember the refractive index N is equal to C over V. What is C? Well, C is what we use to symbolize the speed of light in a vacuum. So the value is there. It's a bit of a coincidence that it rounds to 3 nicely. And we give it the symbol C because it's so important. In fact, you might remember it from the ultimate of equations, E equals mc squared. That C there refers to the speed of light. As you remember from standard form, 3 times 10 to the 8 basically means 3, followed by 8 zeros. So that's pretty fast. If you want it in kilometers per second, get rid of those last 3. Put a K there. So it travels 300,000 kilometers every second. So light is pretty fast. Despite that, it still takes 8 minutes to get here from the sun. Describe the typical properties of the different regions. Well, that's just learning some uses. So you can read those. You just got to learn them. And safety, particularly around microwaves and X-rays, which we'll talk about in a minute. Let's have a look at this spectrum that we've been talking so much about. Here it is. Well, here's one form of it. You can show it in a number of different ways. Let's just talk about a few things. One, we've got frequency, which we symbolise with the letter F. Chemists use that sort of V shape, which is actually a Greek letter. We use F. We've also got wavelength here. Remember, we use lambda to symbolise that. And the wavelength gets larger as we go to the right. Frequency gets larger as we go to the left. And we give different frequencies and different wavelength groups names. These are just human constructed names that we've given to them. You could give them any sort of name, but you've got to remember this is a spectrum, so it's continuous, but we've just chunked it up into groups and give them names. The part over here on the left, which has this weird symbol, is called gamma. Gamma has the highest energy, and the highest frequency. Energy and frequency are related. Higher frequency means higher energy. So the waves look something like that, really close together, short wavelength, high energy, high frequency. As we go further to the left, we get to X-rays and then ultraviolet. In the previous video, we talked about the visible spectrum. You can see it only makes up a tiny part of the whole spectrum, and we said that ultraviolet was next to the violet end, which is over here. And you can see the visible spectrum shown in more detail down here at the bottom. We talked about in the last one, Roy G. Biv, to remember the order. Just after red, we stop being able to see things again and we head into the infrared. So IR stands for infrared, part of the spectrum. Then into the microwaves, and then this whole region that we just call the radio waves, which is broken up into different parts. You might have heard of AM, FM. You just need to know it as the radio wave part. So now that we've gone through the order of the spectrum, and you can see that you just need to learn that, but you need to learn it in order. You need to know which have the highest frequency, highest wavelength, highest energy. Now we've learned about the order. Let's talk a bit about the uses. Well, for the uses, the best thing to do is just go up to the syllabus and learn some of the uses. Some are obvious, some you just are slightly odd, but you just got to learn them. For example, you may or may not know that your remote uses infrared. In terms of the energy, now remember gamma's got the highest energy, so that means it's going to be the most dangerous. Something with high energy, as we know, is going to carry a lot of energy. It's going to cause the most harm to you. Radio waves, very low energy at the other end of the spectrum, and that's why we use them for broadcasts. So I'm going to talk a bit about the last syllabus point earlier, which is demonstrating awareness for the safety issues regarding the use of microwaves and X-rays. So first let's talk about microwaves, and the way to understand the danger is to think about what they do to food when you put that delicious meal into the microwave? Well, what it does, microwaves are beamed in from the side, and they are at just the right frequency to excite water. H2O, it's water, made of 1 oxygen and 2 hydrogens. And actually this frequency is just right to make these atoms vibrate. So here's a little atom of water vibrating. And remember, all vibration is, in terms of physics, well, there's lots of things it is, but one thing it is that corresponds to heat. The more something vibrates, the hotter it is. So microwaves work by making water molecules jiggle or vibrate more, which is heat. In fact, you can test that by putting a food with absolutely no water in the microwave, and it's quite cool. Well, it's not cool because nothing happens. It doesn't heat up at all. It has to have water in, and you might have noticed that it's like a nice sticky toffee pudding. It's normally the centre bit with all the gooey, liquidy bit that gets the hottest, because that's where the most water is there. So what danger is this to humans? Well, if you remember, humans are a good 70% water. So what it can do is it can cause internal heating or burns. Remember, you need the word internal. It doesn't burn the outside. It gets your water hot, which burns you internally. You kind of almost boil from the inside out. So that's why your microwave has, as you guessed it, a nice metal cage along there. It also switches off automatically when you open it, so you can't be exposed to it. This metal cage has little holes which cause the microwaves to diffract. We'll talk about in a future video, and therefore can't cause you any harm. Right, let's talk about X-rays now. Now, X-rays are down in the high energy part of the spectrum, near gamma. So they look something like this, much higher frequency, shorter wavelength, compared to radio waves, which look something like that. Nice long wavelength compared to the very short wavelengths there. Now, what's the problems with X-rays? Well, when an X-ray passes through your body, what it can do is ionize your DNA. Now, it might not sound that bad, just becoming an ion. Well, an ion, as you might remember from chemistry, is when an atom becomes charged. So electrons are knocked off or added to it. Now, the problem with this is, if you ionize your DNA, that can ultimately lead to mutations. We're not thinking X-Men sort of mutations like we see in the films where you can bend metal. Well, most of the time, the mutations just cause the cell to die or to be gobbled up by your white blood cells. But sometimes, in very rare cases, especially as you get older, these mutations can cause your cells to multiply. There's one cell, has a little mutation, and it starts to multiply uncontrollably. That's a tumour. A load of your own cells which have a mutation, which means that they multiply uncontrollably, and this can cause problems, as you are aware. So what do we do to avoid this? Well, you rarely have an X-ray. X-rays are only reserved for serious cases. Now, they'll do it when the benefits of having the X-ray outweigh the small, tiny extra chance of you getting ionized DNA, mutations, and cancer. So it only happens for serious cases when the benefits outweigh the small risk associated with it. The other precaution doctors take, as you can see now written here, is he or she will leave the room when the X-ray is on. This is so they don't get exposed to excessive X-rays. They may also stand behind a lead shield. This is because lead is really good at absorbing X-rays, so it doesn't pass through that. So these are the key 2 ways that we avoid X-rays, and we protect ourselves against them. Now remember, you do need to know use and property for each part of the spectrum, so radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. So go online, look in your notes. You do need to know something about each part and a use as well. Thank you for watching.